Alright guys, this is part 2 of the FFT implementation for audio programmers series, and today we're going to actually take what we did last time, which was solve for a n log n version of a polynomial solver. So we have this one that is big O of n squared, which is the traditional way of doing it, and we have a recursive n log n version, and we are going to use this sort of stem as a basic outline for our fast Fourier transform implementation. But in this video, the fast Fourier transform is going to give you the Fourier transform of a particular bin, and not all of them. And we'll work up to that. But for now, that'll make the most sense because that'll align with like x, as you can see here. We're going to try to retain as much similarity as possible so you can see how this algorithm was really derived. Alright, so let's go ahead and get started. So again, I have the file open from the last video. Looks like I need to redo this. Okay, good. And as you can see, they both result in the same value. Just one of them does it in O of n squared, one of them does it in O of n log n. Alright, so we want to now create a discrete Fourier transform that follows this same pattern, where we give it some x value and it gives us the answer to it. And we're going to relate x to be the bin that we would like the Fourier transform of, and the coefficients are going to correlate to the samples that we give the Fourier transform. That's basically it for the analogy. Most of the steps are the same with the evens and odds and such. But let's go over a little bit of theory to how we can practically do this in programming. So I am no artist, but here is a little visual understanding of how we can derive a Fourier transform version of our evens and odds divide and conquer algorithm. So we have the evens and odds, right? So evens plus x times odds is our general formula that we've been using. But if you remember, the Fourier transform really has two components, the real and the imaginary components. So it is a two-dimensional operation, right? So down here in this next line here, I have the two-dimensional version of that. And you can see that I've substituted x with e to the I omega sub x. And I probably shouldn't have put x. I probably am going to replace that with b now that I think of it, because I have x and y here to show that these are two-dimensional values here. And so what does this mean? How can I just substitute x with e to the I omega sub b? And the answer is I have a couple things written off to the side of what this means. So e, this is Euler's identity, I believe. E to the I theta is going to be equal to cosine of theta plus I times the sine of theta. There are plenty of videos on that, right? So I feel like I don't really need to go in on that. So that is what this means. And so now if I sort of substitute that in, right, I can see that this is really a rotation of the x, or a modification, I should say, of the x and y components of the odd value, which is really just a modification of a rotation of the odd value itself as a coordinate pair, abstractly. So how we rotate, right, is this here. This is directly taken from every textbook that shows the 2D transform rotation matrix. And it's just x times the cosine of the angle that you would like to rotate minus y times the sine of that angle And then y, the new value for it, is equal to x times the sine of that theta plus y times cosine of that theta value. And so these are the outputs, and the x and y's are the original x and y value inputs, right? So with these two things, that I can show you guys now what the Fourier transform really is, the formula. I don't think I've even touched on it in any of my other videos, just because I was showing you how to practically do it and what it practically was. It basically means the same thing, but as you can see, we have the integral from negative infinity to infinity, which just means all points ever, which we can't do with samples, right? We don't have that many samples. And it's just using that formula that's going to make it a two-dimensional value, which is going to have real values and imaginary values. And that is why it is e to the negative I omega t. If you've seen it before, of course, integrating with respect to t, and omega would be like the particular sampling frequency that I've shown in my other Fourier transform videos. And then in discrete version, right, again, I've done this many times before too. It's just the sum of all the sample points, right, and this is for a particular bin, as you can see here. You sum all the sample points, or you sum all the products, I should say, sorry, of the sample points, and this is both a real and imaginary part to it, right? So that's why we end up with two values, the real and imaginary one. And again, I've done this before too. I've got 2 pi n over n, that's going to, and then times the bin, which ends up becoming the sampling frequency, right? 2 pi bin over n is the sampling frequency, and then you multiply by little n to get the position of that wave that we're sampling with. Okay, so yeah, that's a lot of math. I'm not going to go too much more into it. It'll take too much time, and I'm also not that bright, but as you can see down here, this is what we're going to end up using for our formula. This is going to be the basic implementation where we have our even value, right? This is what this means, our even value, right? Working purely with that, we're going to do the rotation, right? We're going to apply a rotation with omega, and then we just use this same exact rotation formula over here with that, right? And now y is x and y are replaced with the the x and y components of the odd value, and then the y coordinate of the evens, right, is just going to be that value, right, plus the second part of this rotation formula, which is just going to be x, which is the x value of the odd value, plus the y coordinate of the odd value times cosine of omega. And again, just look at this, and you don't really need to understand it, but this is how I'm coming up with this code right here. This is a rotation occurring right here. This is a rotation, right? Okay, so that's how we're going to convert this sort of very abstract, basic, recursive divide and conquer algorithm with even and odds into something that we can actually code in 2 dimensions, right? Because this is what we ultimately are going to use abstractly, and this is what we are going to actually implement. And as you can see, it's an array with 2 values, the real, or x, and the imaginary, or y component. Okay, so that's enough theory. Let's get actually into this. So again, to make it as similar as possible, I'm going to actually just duplicate this function. All right, and we're going to call it solve dftr. I'm not going to call it FFT just yet because we're only solving for one bin right now. And so I'm just going to, and now we're going to have different, these parameters are going to be different, right? X is actually going to be the particular bin we choose. So I'm going to make it 0 for now. And we need to change our coefficients. So I'm gonna say let DFT coefficients, and we'll make them equal to these values, right? But we're gonna have to make them two-dimensional, because remember, when we send in a signal to the Fourier, a discrete Fourier transform, it has real and imaginary components. Although when we send it in forwards, the imaginary components are all zero, but it still has them. It is a two-dimensional operation. So I'm just going to add them in. I apologize for the time this takes. All right. So now we have our DFT coefficients, right? So this is what we're going to send in here. Now, we are going to send in a bin, right? And we're going to get a real and imaginary component that corresponds to that bin in the Fourier transform, right? So that means that we're going to be returning a two-dimensional array, right? One real and one imaginary component. So what I'm going to do for now is just turn this into, I'm actually going to keep this, but I just want to emphasize that this is a two-dimensional component that we're going to be returning. Okay, so now we just need to go through and see what we have, right? So we're going to return, ultimately we're going to do the whole evens of evens of evens of evens, right, until we get to our first base case. And then we're going to return the first coefficient, or the only coefficient at this point, right? But this is actually a two-dimensional coefficient. I know that's hard to think about, and really it contains two coefficients in this extended analogy. But it's going to return this, okay? So this is no longer returning a single value, it's returning a two-dimensional value, right? Or it's going to return an array with two values inside of it. Okay, so we're going down, and the next thing that we need to do is actually get rid of this. We don't want to square the x every time we go through, because we're not solving a polynomial anymore. That's not our objective. This is our bin number, and we want to keep that constant all the way through, because we're not going to change the particular bin we're solving for. So I'm just going to change this to x. So bin is constant. Right? Okay. Now this process remains the same, but keep in mind, now we're returning a two-dimensional value. So this now holds two values, and this now holds two values. Oh, whoops, I scrolled too far up. I'm gonna copy this, and apologies, I scrolled up to the previous one. I'm gonna put some space. All right. So, just making sure everything's still good, right? Okay, so now we're gonna get into the applied theory part, right? So we're solving for even plus x times odd, right? And we found that it's really this, according to our theory. The even coordinate, and then we found that we really just need to return this, right? So I'm going to call this the real value, and this the imaginary value. So, and right, and then we're returning that two-dimensional array. All right, and so this is what happens. This is the result of this operation. We're going to take the, well, first off, we should probably calculate omega, right? So let omega, and what is this equal to? Well, I wrote that over here in the theory part. That's going to be equal to -2 times math.pi times our bin frequency divided by the length of coefficients. Right? So that's that. And then I'm actually going to hop over to our original FFT code. This is surprisingly all we really need to do. So let's just reference it. We don't need to copy it. But as you can see, we're doing this summation with this real sum and imaginary sum. We don't need to do that because we're doing it recursively already, right? Or that's what we're going to do. When we return this real value and this imaginary value, we're going to use those in these operations, right? That's going to be our even value here, right? That's what that's going to be. So we are going to be summing, in fact. But we don't need this plus equal to notation because we're doing it recursively, right? So just looking at this, we can see where they correspond. We have this even value already here and here, right? The even, or the real and imaginary parts of the even values. And then we're adding on the cosine of omega. And then this is just for the actually different bins, right? But we don't need different bins. We're just solving for one bin. And then we're solving with the real and imaginary odd values, right? That's all this is. This is a direct correspondence to this, right? The code is virtually the same. So I can actually copy this over, although I'm not going to do that. I'm just going to copy the line and then just update what I need to update. So first off, I told you we need the even value, right? So evens value, and that we need the real part, right? In this particular thing. And then I'm just running from here, right? This is where I'm coming from. And then we're adding the cosine, right? Which is being done over here, except we don't need I, we already have our sampling frequency. And we're multiplying that by the real component of the odd value. So just odd values of 0. Right? And then we're subtracting the sine of that, of omega, times the y value of the odds. So that's just going to be odd value of 1. Right? And then if I copy this part from here, we're going to be using the imaginary part of even value, which is going to be evens value of 1. And then I'm basing this off of this formula over here. And just in case you can't see with my face down there. And then we are adding the sine of omega times the x value of the odd. So plus, I guess I'm going to copy this now. Right, so the sine of omega times the real component of the odd, and then we're going to add, right, the cosine of omega and plus the imaginary component of the odd. All right, and then we have our real and imaginary values, and then we're just going to return them. And as you can see, when we do this, right, we are using these values here, right? Just that's a level lower in recursion. We're using these values. And ultimately, we're just returning them until ultimately we will return the actual Fourier transform for bin X. So let me reorganize my screen. All right. let's see, let's just make sure that I did everything right. Bin is 0. Looks like I've made a typo or something. Evens value 0 plus odds value 0. That's the cosine of omega. And let's just make sure, oh yes, so we need to actually replace the recursive call with this particular one. And as you can see, right, that was a huge mistake on my part. But as you can see, we have 36 and 0, which does correspond to bin 0's Fourier transform real imaginary components. And then we have -4 and that number. And then we have -4 and 4. -4 and that number. -4 and 0, I guess. And anyway, if you really want me to go through it, I can pull up a actual Fourier transform calculator. And it's just 1, 2, 8. And as you can see, those values aligned, right? Go through. All right, so yeah, that aligns well. That's bin 2 and that's doing that. So look, guys, we have now just taken that n log n algorithm that we found for just solving a polynomial, and we have now turned it into a working, not quite FFT, but a particular bin frequency solver, or Fourier transform for a particular bin solver. And it's very, very similar to the polynomial solver. I mean, I copied the function and just changed only a couple things, and we had to go from 1 to 2 dimensions, but with the theory I showed, hopefully that makes sense. But yeah, we have now done this, and we've solved the, we're really close to the fast Fourier transform. In the next video, we're going to just change the way that we are solving this so that we actually solve for every single bin frequency, which will be the Fourier transform, which will be the fast Fourier transform. So yeah, I'm really excited because next video we'll have our first working fast Fourier transform.